So now that we've covered some of our basic forms, let's talk about some non-basic forms. The first non-basic form that I wanted to talk about is one that contains a frequency modulation. So same basic form of sine, cosine, or tangent of an angle is equal to a constant. But this time, instead of just theta on the inside here, we would see something times theta. So this is where n could be a multiplier like 2, 3, 4, etc. Now just as a quick reminder from the graphing sections, when we talk about y equals the sine of x on 0 to 2 pi, first full period of the sine function looks just like this. So regardless of the value of c, chances were pretty good we were going to be able to find two solutions for it. However, if we were to consider y equals the sine of 2x, then in between 0 and 2 pi, we are now going to be able to fit a total of 2 periods of the sine function. Which means that if we set it equal to a value, there should now actually be a total of 4 solutions for it. Whereas if we had y equals the sine of 3x, then between 0 and 2 pi we can now fit 3 full periods. Meaning that if we set the sine equal to something, chances are pretty good we're going to find 6 different angles where this takes place. Now, in the previous video, when we talked about the general solution, we talked about adding a plus 2k pi to this. The significance of the value of the k is referring to which period you're at within 0 to 2 pi. Now for the sine of x, that has no impact whatsoever, because there's only one period in there. For the sine of 2x though, because we're fitting 2 periods in here, the first one corresponds to k equals 0, the second one corresponds to k equals 1. Now between 0 and 2 pi for sine of 3x, there are a total of 3 periods present. First one corresponding to k equals 0, then k equals 1, then k equals 2. Now generally speaking, the values of k that are going to be valid are going to start at 0 and go all the way up to one number before whatever the multiplier is. Just to give you a quick example of this, consider the sine of 3x being equal to positive 1. Now this occurs at only one spot within the unit circle, and that's when the angle is equal to pi over 2. Now our angle in this case is 3x. So quickly, I'm going to make a little substitution and say let theta be equal to 3x. Then we're simply solving the sine of theta is equal to 1. And again, there's only one place that this occurs, and that's at pi over 2. However, what we're going to do is copy down the general solution. That's because when we substitute back, there's now going to be some additional algebra to do. Specifically, it'll be to divide both sides by 3, or since we already have some fractions in here, multiply both sides by 1/3. So this will be pi over 6 plus 2k pi over 3. Now according to what we said back here, there should be a total of 3 values of k that will produce a solution within 0 to 2 pi. If we plug in k equals 0, this would simply be pi over 6 plus 0. So x would be equal to pi over 6, which is in 0 to 2 pi. If we plug in k equals 1, this would be x equals pi over 6 plus 2 pi over 3. After getting a common denominator for these and adding them together, that would be 5 pi over 6. And for k equals 2, this would now be pi over 6 plus 4 pi over 3. Once again, we get a common denominator of 6 and add them together, we get 9 pi over 6. 9 pi over 6 reduces nicely to 3 pi over 2. All three of these angles are within the first full rotation of the unit circle. However, you'll notice that if we were to try k equals 3, we would be getting x is equal to pi over 6 plus 6 pi over 3. And I can guarantee you that because we're adding 2 pi to this, this is not going to be in the appropriate interval. Therefore, only 3 values of k should be working out. Now, to demonstrate this with a slightly different example, let's consider the following. The cosine of 4x is equal to negative 1/2. So as we did before, I'm going to make a substitution on the angle and let theta be equal to 4x. By doing so, we're now solving cosine of theta is equal to negative 1/2, which is one of our basic forms. What I'm going to do is find the general solution of this. That way we can allow the frequency modulation to occur. There are 2 angles on the unit circle where the cosine is equal to negative 1/2. There will be a quadrant 2 angle as well as a quadrant 3 angle. This will occur at theta is equal to 2 pi over 3 or theta is equal to 4 pi over 3. Writing these down as general solutions, this would be theta is equal to 2 pi over 3 plus 2k pi, or theta is equal to 4 pi over 3 plus 2k pi. Substituting back, the original substitution was theta is equal to 4x, so 4x is equal to 2 pi over 3 plus 2k pi, or theta is equal to, 4x is equal to 4 pi over 3 plus 2k pi. Continuing to solve for x, I multiply both sides by 1/4, and I get pi over 6 plus k pi over 2. Again, multiplying by 1/4, we can reduce the 2's. Or x is equal to, this would be pi over 3 plus k pi over 2. Now there should be multiple values of k that, when we plug them in, should work out. In fact, there should be a total of 4 values of k that we plug in, starting at k equals 0. So for k equals 0, we would get simply x is equal to pi over 6 or pi over 3. For k equals 1, we would get x is equal to pi over 6 plus pi over 2, which, when simplified, gives 2 pi over 3. And from this one, this would be pi over 3 plus pi over 2, lowest common denominator of 6, and add them together. That would be 5 pi over 6. At a value k equals 2, this one gives x equals pi over 6 plus 2 pi over 2. Getting a common denominator gives us 7 pi over 6. And this one would give pi over 3 plus 2 pi over 2. Common denominator for those, we get 4 pi over 3. And finally, k equals 3, we would get x is equal to pi over 6 plus 3 pi over 2. Get a common denominator for those, add and reduce. We'll get 5 pi over 3, or pi over 3 plus 3 pi over 2 from this solution. That'll be 11 pi over 6. Anything beyond those, and we would be outside of the range of 0 to 2 pi.